Show using vectors that the lines connecting each vertex of a tetrahedron to the centroids of the opposite faces intersect at a single point. Okay, now let's try to understand this problem graphically first. So here we have a tetrahedron. We're going to consider the vertices as A, B, C, D. Now, a tetrahedron consists of four sides. One will be, each side represents a triangle. So we have the triangle ABD, we have BDC, we have ABC and ADC. So these four triangles forms a tetrahedron. Now, we need to show that the lines connecting each vertex of a tetrahedron to the centroid. So let's say if we consider ACD, the triangle, the bottom triangle, and let us suppose that G1 corresponds to the centroid of ACD. So centroid is a point which is going to be the point of intersection of the three medians of the triangle. And then we're going to join B and G1. Next, let's consider the triangular face BDC. And let's say that G2 is the centroid of the triangle BDC. Then the vertex opposite to the triangle BDC, that's vertex A, we are going to join A and G2. And then we can consider the rest of the two centroids, and we have to show that all of the four lines are going to intersect at a single point. So let's say this is the single point P. We need to show that these four lines are going to be concurrent. Okay, let us begin. First, we are going to consider a point O, which is going to be an origin. Now, with respect to this origin, we can define the position vector of each of the vertices of the tetrahedron. Now, let us suppose that OA vector, so this is going to be the position vector of vertex A. We're going to denote it by the vector A. OB vector is going to be B vector. OC vector, let this be the vector C, and OD vector, let this be equals to the vector D. So let G1 be the centroid, G1 be the centroid of the triangle ADC. G2, let this be the centroid of triangle BDC. Then we consider G3 to be the centroid of the triangle ABD. And we have G4. So let's say G4 is the centroid of the triangle ABC. Okay. Now let's start with the triangle ADC. Now in triangle ADC, we can define the position vector of its centroid OG1 because there's a standard formula for it. All we have to do is consider the position vector of each of the three vertices of the triangle. So that's vector A, vector C, and vector D. So we're going to take the sum of these three vectors, A vector, C vector, and D vector, and divide it by 3. Next, we will consider the line BG1. So here we have to remember a fact. We have to remember that this particular point P divides BG1. So that is the line joining the vertex B with the centroid G1 in the ratio 3:1. Now we have to remember this particular fact that the point P divides BG1 in the ratio 3:1 internally. So that means here we can apply the internal section formula. So that means the position vector of point P, so that's going to be equals to, so we'll take 3 and multiply it with OG1 vector, add it to 1 times the vector OB, divided by 3 plus 1. So let's use OG1 vector. So here, with this is OG1 vector, that will be equals to 3 times the vector A plus vector C plus vector D, all divided by 3. Add it to OB vector, so that's going to be the vector B, whole divided by 3 plus 1, so that's 4. So that gives us OP vector as A vector plus C vector plus D vector plus B vector divided by 4. So this is going to be the position vector of the point P. Now, next, if we take the triangle, let's take the triangle BDC, then the centroid, we already have the coordinate of we have the position vector of the centroid G2, so that will be D vector, C vector, P vector, their sum divided by 3. Again, we'll use the fact that P divides AG1 into ratio 3:1. When we apply the internal section formula, we'll see that the position vector of this point P again comes out to be the sum of the 4 vertices of the tetrahedron divided by 4. Similarly, if we consider the other 2 faces of the tetrahedron, we can show that the position vector of the point P again comes out to be the sum of the position vectors of the 4 vertices of the tetrahedron divided by 4. Hence, the line connecting each vertex of a tetrahedron to the centroids of the opposite faces intersect at a single point. Hence proved.